Hello. We made this video to show you something important. With just a little bit of STEM knowledge, science, technology, engineering, and math, and a spark of creativity, you can make amazing things happen. You don't need a huge lab or a pile of expensive equipment. You just need some curiosity, some basic tools, and the willingness to experiment. The Ratty Rover is a perfect example. It started as a simple idea. What if a rat could drive its own little car? By combining a few electronic parts, some clever code, and some imagination, we built a real working rover that responds to touch and lets the rats drive it around. Now, the goal isn't just to show you a cool project, it's to inspire you. Because the same way that we made this little rover, you can take your ideas, no matter how silly or wild they sound to someone else, and you can bring them to life. And that's the power of STEM and creativity working together. So here we go. This is a friend of mine named Blair. She owns a couple of rats, and one day she happened to be prowling some kind of news feed and she came across an article by the University of Richmond. It was about a group of scientists from the University of Richmond who were doing a study on mental health, and they were using rats driving cars as an example of what would happen if a person's environment was stimulus rich.
Our lab is interested in something we refer to as experience-based neuroplasticity. So we're interested in how our environment and our interactions with the world sculpt our brain, our neural networks. And this could have some therapeutic value as we learn more about this and helping us understand mental illness and mental health. And our collaborators are the rodents. We have a rat lab here at the University of Richmond. Their brains have all the same areas that our brains have and neurochemicals, so it's a good starting point model to use to learn more about the human brain. We love to study these animals and see, we're always amazed at what they can do in the lab with their behavior, their cognitive flexibility, their emotional resilience. We follow the rodent behavior and their brains to learn more about human behavior and brains. When we published the original driving rat manuscript, part of that was looking at the effects of different environments on the animal's ability to drive. And we've been interested in enriched environments in other areas of the lab research areas. And when I say enriched, I mean an engaged environment, more engaging and dynamic than the standard rat laboratory cages. So in an enriched or an engaged environment, the space is larger, there are more animals in there to interact with, they can exercise, we introduce new stimuli, some of them are more natural stimuli as well. So we think it's closer to a natural environment for the rat. It's no real surprise that they train more efficiently, that they're more motivated to drive the cars. We're also interested in measures or markers of neuroplasticity, and we have a grant from the National Institute of Mental Health to look at ways to enhance emotional resilience in the rats so they may be less susceptible to show evidence or behaviors that are consistent with depression or anxiety disorders. Neuroplasticity, the brain's ability to change, seems to be important for emotional resilience and for cognitive abilities. And so we're beginning to think about how we can look at markers for neuroplasticity in these driving rats. This is a big part of their life that where training is happening. And we know even with humans that training can change the brain in really interesting ways. Just learning to juggle can increase the density or the area of certain areas of our brain's cortex. There's been a lot of interest in this, and so it's just fun to see a rat driving a car, but in the context of sharing that with someone or an audience or writing about it, I have an opportunity to talk about the impact of enriched environments, to talk about individual differences, to talk about sex differences in learning, the impact of training, healthy brains throughout the lifespan. So it's become a great springboard to talk about some of our laboratory research.
So that was all very interesting, but what Blair really wanted was her own Ratmobile, a Ratty Rover, a car that her rats could drive around. We looked on the internet and there were no companies that build this kind of thing. So fortunately, the university staff put together a very rudimentary set of instructions about how they built their Ratty Rover. They weren't amazing, but looking at those, we decided that it was going to be possible for us to build one as well. And so let's talk a little bit about how we did that. The instructions to be able to build the rat operated vehicle are pretty sketchy, but they are available. www.instructables.com, rat-operated-vehicle. And so these are the instructions that were put out by the University of Richmond. And so as you scroll down here a little bit, you can see that they've got a list of supplies right there. Um, and some of these things we used, some of these things we did not use. A lot of this stuff that they're listing here comes with the Rover kit. So you don't have to use all of that, but things like bare copper wire you're going to need. And then some of these tools right here. So as you come down, it'll tell you sort of step by step, give you some instructions on how you can wire these things together. They have some sample code here. We didn't use this code. We used some of our own code, but this is certainly something that you can use as an example of how you can program the Arduino using the developer's environment. So the first thing we needed to do was to buy the rover itself, and it costs, as you can see, about $80. We bought this one off of Amazon, but it's made by a company called Elegoo, and we bought the Uno R3 Smart Robot Car Kit version 4. And you can see that it's just a STEM kit for students that are ages about 8 to 12. The truth is, you don't need version 4 of this. You can probably get away with some of the earlier versions. Version 4 has some things such as a camera, which you can see is at the top. It's a little item at the very top, and then it's got two silver things that look like eyeballs. Those are sensors that will tell the rover when it reaches an obstacle, and it will cause it to avoid that obstacle. We don't have any of those on ours. The other thing it has at the bottom, you can see that there are two little metal points at the very bottom of the rover there. Those metal points will allow it to follow a line. So you could create a pathway on the ground and the rover will follow that. But this rover is designed to be used by a person with an app. And it was not designed to be run by a rat. So we had to do some modifications. So the first thing that we did was that we took off all of the sensors that were unnecessary. So here's a picture of the assembly of the rover, and it took us maybe an hour, perhaps 90 minutes to put the whole thing together. It was really quite simple. The instructions were very, very clear. They were very straightforward. The first thing that I want to start with once the rover was assembled is I want to start with the brain of the rover. It uses something which is called an Arduino. It's a small computer, but unlike the big computers that you're used to, the Arduino only runs very simple programs. We write those programs in a language called Arduino C++, which looks like some of the code that you're familiar with, perhaps, if you've ever done any coding for any of your STEM projects. But this specific code is made only for electronics. And when we upload that code, the Arduino remembers it, and of course, it runs it over and over forever. The next step in the process is to go to www.arduino.cc/en/software, and this will give you access to the free software, which is the Arduino IDE. The IDE is your developer's environment, and this is going to allow you to create the code that you can then upload to the rover. And once you download that software and you open it, this is what the development environment looks like. And you can see that you've got your different lines of code. It looks just like any kind of developer environment that you would normally use, even if you use Scratch. It's got a very similar feel to that, except that it is text-based rather than visual-based. And so this particular code we wrote, it's not difficult to do. You can certainly learn it yourself. You're quite capable of doing that. If in the event that you are having a hard time with it, you can consult a large language model like ChatGPT, and it will help you work through the code as well. to get it to do the things that you need it to do. So what does the Arduino actually do? Well, its main job is to control electricity. So imagine that the motors that are on the bottom of the rover spin the wheels, but they don't just turn on and off. Instead, what happens is the Arduino sends them signals that go up and down in voltage very quickly, and we call this pulse width modulation, or PWM. By changing how much time the signal stays high or low, we can make the motor spin faster or slower. Higher duty cycle is equal to faster turning of the wheels. Lower duty cycle equals slower turning of the wheels. So the question now is, how does the rat tell the Arduino what to do? And that's where our touch system comes in. So inside the rat's cabin, which is just a plastic container made to hold cheese balls, cheese puffs, there's a brass plate connected to the ground. And by the ground, I don't mean the dirt underneath your feet or the floor underneath your feet, but rather the ground is the 0 point of the circuit, if you think of it that way. And the brass plate is just a brass hinge that we bought from Home Depot, along with all of the other pieces like the acrylic platform that the cabin sits on, and the PVC piping, which are the stands that elevate that acrylic. All of that was just purchased for a couple of dollars from Home Depot, along with the copper wiring that we use for everything. So in front of the rat are 3 control bars. One is wired for forward, one is for left, one is for right. And each bar is connected to the Arduino by a thin copper wire. So what happens is when the rat touches the brass plate and he touches a bar at the same time, his body completes the circuit, just like when you close a light switch. That little bit of current makes the voltage on that pin drop. And here's an example of what a pin looks like. The pin is just a place where you connect the wire from the copper bar on the cabin of the rover. When the voltage drops, the Arduino notices the change. We call this using pull-ups. By default, the input is high, but when the circuit is closed, through the rat, the input falls to low, and the Arduino reads that as a signal. So once the Arduino senses which bar is touched, then the code in the Arduino decides what to do. If the forward bar is touched, then it sends power to both wheels either side, and then that sends it home, or that sends it forward, rather. And then if the left bar is touched, one set of wheels goes forward, the other set goes backward, and then the rover pivots to the left. If the right bar is touched, the opposite happens, it pivots to the right. And if no bar is touched, if the rat just sits on the ground on the metal plate on the bottom, the Arduino cuts the power and the rover stays still. So in the end, the whole system is really very simple. The rodent's touch closes a circuit, and the Arduino senses the drop in the voltage when that circuit is closed. The code in the Arduino decides the action based on that drop, and then the motors respond by changing the voltage to spin the wheels, and that's it. And so the best part is we tested it with actual rats, and they were able to drive the rover around just by touching the bars. So Ratty Rover is alive and rolling. So I wanted to say thank you for watching our Ratty Rover project, and we hope you had fun learning how we combined code and circuits and creativity to bring this little idea to life. Remember, projects like this don't have to be complicated or perfect to be fun and amazing. The most important part is to be curious, try things out, learn along the way. Every big invention in life starts with someone who wasn't afraid to tinker, to experiment, to make mistakes. And so I don't want you to be afraid to try your own STEM projects, whether it's coding or building or inventing or doing something that's brand new. You never know what kind of cool ideas you can bring to life. So thanks again for watching, and now go out and make something awesome.